For those of you who live in the blissful state of never watching the news, Texas just recently got hit with a cold snap, the likes of which we almost never see. In fact, one of the nights in that cold snap recorded the second coldest temperature ever recorded in Texas history. The previous coldest one was in 1889. And then the power went out. So we got to experience it exactly like they did. Now, I was struck by a couple of things during the storm. One was how fast you actually do kind of get used to the cold. I was out shoveling my driveway at one point and realized I was fairly comfortable even though it was only 25 degrees outside. And the second thing that struck me is that that level of cold and much, much colder is the actual state of the universe. The warm, humid thing that we get to live in, this biosphere that we live in, that's the aberration. You know, if it wasn't for the greenhouse gases that are in our atmosphere that trap that heat, we would actually be colder than we normally are, like much colder. In fact, this happened once before. They called it snowball Earth. Now, granted, we have the opposite problem now with the buildup of carbon dioxide leading to excess heating and whatnot, but carbon dioxide has become a bit of a pariah for that reason, and understandably so. But I don't know, maybe we should be giving carbon dioxide more credit. You know, God bless carbon dioxide. Up to 300 parts per million. You know, it just goes to show that there's some very specific conditions here on Earth that make it a nice little sanctuary for us to live in, because the rest of the universe it's pretty weird. You know the sun, that big flaming ball in the sky, we typically expect it to pop up once a day. But what if it didn't? What if you woke up one morning and the sun was just gone? If you were living on a planet orbiting around the star I'm about to talk about, that's exactly what you would have experienced. The star, it doesn't seem to have a name, was a luminous blue variable star, or LBV, located in a dwarf galaxy about 75 million light years away. Note I said was, because, yeah, it's not there anymore. And this was no small star. It was 2.5 million times brighter than our sun. And it showed up in telescope data from 2001 to 2011, and then in 2019, scientists went to go look for it, and it had just vanished, just wasn't there. Looking back through the archives from the European Southern Observatory's Very Large Telescope, they saw data from 2001, 2002, 2009, and 2011. And the data suggested it was spewing radiation, which is the sign of a dying star. And then in 2016, the data just stopped. Stars don't usually do that. Stars of that size usually go boom at the end of their lives. Stars exist in a balance between gravity pulling in and radiation pushing out. When radiation takes a nosedive, gravity wins and the star collapses. And this triggers nuclear fusion, the boom that I mentioned. Outer layers of the star are flung outward in a supernova, which is one of the most spectacular sights in astronomy. In fact, that's why astronomers were keeping an eye on it. They were expecting it to put on a show. That show turned out to just be a vanishing act. Somewhere between 2011 and 2016, against all the laws of nature, this star just pulled an Andy Dufresne.
Man up and vanished like a fart in the wind.
So did this star just sneak off to a cosmic Sewatenejo or what? What happened to this thing? So one theory is that it shed just the right amount of radiation to make it go dim, but not go boom, and then sort of a cloud of dust covered it up after that. Now this scenario is unusual, but it's not as unusual as the idea of a star of that size just collapsing down to a black hole without going supernova. No star has ever been observed making such a gentle collapse. And that doesn't mean that it can't happen, just that we've never seen that happen. Which brings us to a third theory, which is maybe it did go supernova, and we just missed it. Now that could be the case if it was a supernova that occurred last century. There is the possibility that it actually went supernova a long time ago, and what we've been observing from 2001 to 2011 was actually a dying corpse. So by this rationale, the star went supernova sometime in the 90s when we weren't looking. And then what we saw and thought of was an LBV was actually a supernova remnant that was kind of mimicking an LBV. Or to quote the research paper by Andrew P. Allen of Trinity College Dublin, quote, "The broad components seen in the Balmer lines between 2001 to 2011 would have come from the interaction between the SN ejecta and a dense circumstellar medium." Now all three of these theories are actually pretty unlikely, but something happened to that star. So here's hoping that when the extremely large telescope comes online in Chile in 2025 that maybe we'll shed some light on it. Because that star's not shedding any light anymore, am I right? From a star that should be where it isn't to a particle that shouldn't be where it is. In 2006, NASA scientists in Antarctica found what may be a clue to a parallel universe. Or dark matter? They were using a telescope called ANITA, which stands for Antarctic Impulsive Transient Antenna, which is an interesting little telescope because it actually is suspended by a balloon. And it was designed to detect high-energy neutrinos from outer space. Neutrinos are a fundamental particle in the Standard Model that are very small and electrically neutral. They're also some of the shyest particles because they barely interact with matter. It takes a very high energy particle to even be detectable by the most sensitive equipment, and that's kind of why they're down there in Antarctica, is because it's got very clear skies and it's a lot easier for a neutrino to come through and not hit something. But what made the neutrino that was detected in 2006 so unusual wasn't that it was so high energy, it was because it came from below. Actually, just to make this more complicated, ANITA doesn't actually directly detect neutrinos. It actually detects a type of radio signal that comes off and gets triggered when neutrinos interact with particles. And this actually does travel up and not down. This is known as Ascarian radiation, and it's basically the optical equivalent of a sonic boom. Sonic booms, of course, happen when a jet or a rocket travels faster than the speed of sound. The sound waves kind of collect behind the rocket and then explode backwards in a cone shape. Well, this is the same idea. When a neutrino goes faster than the speed of light, those light waves pack up behind it and then project backwards in a cone shape. You want to comment so bad right now, don't you? Yeah, I know. Nothing travels faster than light, yes, we all know this, in a vacuum. But in ice, neutrinos interact with matter so little they can actually outrun photons. Which is why they go down to Antarctica to study this, because they have a few ice cubes down there. So as light and radiation come raining down on the ice and snow of Antarctica, the neutrinos flying along with it hit the ice and then send cones of Ascarian radiation up into the air, where ANITA is dangling from a balloon ready to detect them. Okay, you following? You feel a little bit in the weeds? Well then, hang on, we're all about to turn into little Sebastian lost in a corn maze. Okay, so the radiation that ANITA picks up that's coming up off the ground has an electromagnetic charge to it, and that charge is a mirror image of the electromagnetic field in that local area. So what they caught in 2006 was a hit of radiation that matched the local electromagnetic field. It hadn't been flipped like they would have expected it to, but it was the signature of an Ascarian radiation from a neutrino impact, which means that the radiation wasn't traveling up from the ground, it actually came from above ANITA, meaning the neutrino came from the ground. All of that is a complicated way of saying that ANITA detected a high-energy neutrino coming up from the ground. The problem with this is that should be impossible, according to all known physics. Now, low-energy neutrinos pass through matter all the time. There's like 1 trillion of them passing through your thumbnail as we speak. And so those could travel all the way through the Earth. But low-energy neutrinos wouldn't spark light cones because they don't interact with the ice, and no high-energy neutrino would pass all the way through the planet and then suddenly interact with the ice on the surface. And in case you're wondering, yes, there are processes taking place underneath the surface of the Earth, like radioactive decay, that do produce neutrinos, but again, they're the low-energy neutrinos. As far as we know, high-energy neutrinos only come from space. This, of course, led to tons of speculation about what exactly happened here. Over 40 different papers were published on this one neutrino finding. But there was one, of course, that got far more attention than the others. It interpreted the ANITA anomalies as evidence of the CPT symmetric universe, which is the idea that when the Big Bang happened, it actually created 2 universes, one made out of matter that we're living in, and one made out of antimatter. Time in the antimatter universe flows backwards from what we perceive anyway. And there is a theorized type of neutrino in the antimatter universe that would resemble what they picked up from ANITA. In other words, a neutrino sneaked over into our universe from a parallel universe, and what we picked up was a neutrino from a parallel universe hitting the Earth, but traveling backwards in time. Go watch Tenet if you're confused, which will only make you more confused. Now, this is mostly wild speculation. There's not much more evidence behind it to back all this up, but it is something that gets a lot of clicks, so that's what you probably heard the most about. I mean, another team of astrophysicists and glaciologists suggested that maybe ANITA was just fooled by the reflections coming off of some weird snow. And like I said, there's 40 other papers with answers that are just as boring as that one, so one of those probably has it right, because it is usually the more boring answer. That's the right one. Everybody loves talking about Oumuamua. There are thought to be over 1 million asteroids orbiting our sun, with more than 6,000 comets doing the same thing. And it's estimated there could be more than 1 trillion undiscovered comets out on the fringes of the solar system, as I covered in my video on the Oort cloud. So why did one cigar-shaped object that showed up on telescopes back in 2017 get so much attention? It's because it wasn't one of those trillion objects. This particular object was traveling way too fast and in the wrong direction to have come from anywhere nearby. This came from somewhere else. They named it Oumuamua, and it became the first visitor from outside our solar system to ever be detected. But that was only the beginning of its weirdness. Oumuamua moved like a comet, but it didn't look like one. The obvious difference was it didn't have a tail or a coma around it, which is created from outgassing. Which is also the explanation for why comets move the way they do, because they're made out of mostly dust and frozen gas. As the comet gets closer to the sun and these materials heat up and expand, the gas can escape through holes in the comet's core. This works about the same way as a cold gas thruster on a rocket. So comets don't generally fly in straight, perfectly predictable lines. They tend to wobble in random directions from outgassing. It can even accelerate their orbits if the outgassing happens at the right angle. Which is exactly what Oumuamua did as it sailed through our solar system. It accelerated, just like a comet. Only it didn't seem to be outgassing anything, so what caused this acceleration? Astronomers have suggested that maybe it was a type of invisible gas, like maybe hydrogen. In fact, the hydrogen theory works so well that many astronomers think it might have just been a hydrogen iceberg floating through space. Now, we've never actually seen a hydrogen iceberg before, but it's theorized that there could be a lot of them out there. The question is, could it actually reach us? Harvard astrophysicist Avi Loeb says no. According to a paper co-authored by Korean astrophysicist Thiem Hwang, even Oumuamua's closest possible origin is too far away for a hydrogen iceberg to survive the trip. They make this statement in part because they believe that an iceberg like Oumuamua would have had to be formed in a giant molecular cloud. These are star-birthing regions, like the famous Eagle Nebula. The closest is the Taurus molecular cloud, a mere 430 light-years away, but still, Oumuamua would have needed hundreds of millions of years to cross that distance. And the kind of outgassing that we saw from it would have vaporized it completely after 40 million years. But a giant molecular cloud is not the only option for a place where something like this could form. It could have formed in a smaller, more temporary cloud. You know, that cloud could have produced a few icebergs and then kind of fizzled itself out and chunked Oumuamua at us in a sub 40 million year range. But Loeb dismisses this idea too, saying that the conditions necessary to make a hydrogen iceberg would have only been around billions of years ago, so it still would have been way too long for it to have existed. So, now we come to his thesis. I'm sure you all know where I'm going with this. Yep, in a statement that spawned a million clickbait headlines, he said it might be aliens. Specifically, a solar sail, which could explain the acceleration because of the sun's light. It is still controversial, but he lays out his argument in his book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, which just came out in January. And look, it's a compelling argument for Oumuamua, but Oumuamua is a compelling subject. Every single one of the theories around it have their own caveats, and the fact of the matter is, we'll probably never know what the truth is about it. It sped through the solar system and it caught us by surprise, and all we have is a small amount of data that we were able to collect before it got out of our range. So the truth is out there, but we may never know it. By the way, they have confirmed a second interstellar visitor since then, but it is definitely a comet. It's called Borisov. It had a tail 14 times the size of Earth, so yeah, kind of hard to miss. Young is a relative term when you're talking about planetary sculpting. Venus for the longest time was considered Earth's twin. We're roughly the same size, we both have thick atmospheres. Of course, the more we got to know about Venus, the more we realize how much different that atmosphere is. But when NASA's Magellan spacecraft started taking measurements in the early 90s, it became apparent that we had something else in common. Very few craters. Earth, of course, has a water cycle and tectonic activity that's wiped away many of our craters, but Venus doesn't have that. What it does have is mantle convection, which is basically the churning of molten rock underneath the surface. Now, the Earth has that too, and that's what kind of pushes our tectonic plates around, but Venus doesn't have any plates, so that mantle has nowhere to go. And with nowhere to go, that mantle is forced to compact against a hard ceiling, and it kind of builds up and builds up and builds up, and eventually spills over and remakes the surface. The question is how often this happens. And there's two competing theories as to how exactly Venus gives itself a makeover. One is the steady state theory, and one is the global catastrophe theory. If you wanted to make a movie, catastrophic resurfacing would be the obvious choice. Global volcanic meltdown, violent eruptions from pole to pole, lava pouring from the desert to scour the land. The steady state model is less flashy. In this case, it's just volcanic eruptions that occur from time to time and resurface the planet in various areas. There's no big catastrophic meltdown or anything, just an easy, steady flow of lava. Now, both models work. One is just way more dramatic than the other. But which one's right? Fans of the catastrophic resurfacing model claim that one proof that their model is correct is the fact that of the few craters that Venus does have, they're very, very well preserved. In fact, 85% of the craters seem totally untouched by volcanic activity. If a global catastrophe is what made Venus look so young, then evidently very few volcanoes happened after that. Otherwise, they just happened to take place where there wasn't a crater. So the catastrophic model explains this by saying that once the pressure was let off, then it was going to take millions upon millions, probably hundreds of millions of years for that to happen again. So it would happen periodically, but it would take a long time between that. With the steady state model, though, the pristine craters are kind of harder to explain, because there's no reason for eruptions to slow down in a steady state model. So you would think that if there was a gradual state of constant, remaking of the surface, then some of these craters would have been marred by volcanic activity, but that doesn't seem to be the case. So are you a catastrophe nut or a steady state nut? Both models have their passionate defenders, but if nothing else, the mystery kind of adds more reasons to go back and explore Venus. And last but not least is cosmic rays. I talked earlier about high-energy neutrinos and how we found one that was doing something that it's not supposed to do, but that also opens up a broader question about high-energy cosmic rays in general. Prior to the 1930s, it was thought that cosmic rays and gamma rays were the same thing. Gamma rays is radiation that comes off of nuclear decay. And according to the comic books of the day, it gave you superpowers. Of course it doesn't, unless you consider cancer a superpower. Cosmic rays are different. Cosmic rays are particles, usually subatomic particles, but sometimes heavier elements mix in. As with neutrinos, cosmic rays come in different energy levels, with the highest energy levels being the most mysterious. Like the sun throws off beams of protons that can be technically considered cosmic rays, but usually when you're talking about cosmic rays, we're talking cosmic distances, like from other galaxies. Supernovas are a source of cosmic rays, which there's no real surprise there. An exploding star you would think would have a pretty mean pitching arm. But the highest high-energy cosmic rays are even outside of that ballpark. For comparison, the most powerful proton-to-proton collisions at the LHC measure about 7 tera-electron volts. Cosmic rays can have energies of 5 times 10 to the 7th tera-electron volts, 10 million times the LHC's best. I covered the oh my god particle in a video a while back, and that was 4 times 10 to the 7th tera-electron volts. Now, if you're a normal person and numbers like that mean nothing to you, consider the fact that that one single proton was carrying as much energy as a baseball being thrown at 50 miles an hour. And you thought that pitching analogy wasn't going anywhere. The point is that even supernovas, stars that are so bright they outshine their entire galaxies, are too puny to make that happen. I should note that there are some astrophysicists that are way smarter than me that do think that supernovas could be candidates for that, but that is not the general consensus. One possibility is an active galactic nuclei, which I've talked about before on this channel. When a supermassive black hole at the center of a galaxy blasts out a jet of electromagnetic radiation at close to the speed of light, we call that a quasar. When the blast is pointed right at us, and particularly bright, we call that a blazar. Both of these are types of active galactic nuclei, and cosmic rays could come from all of the above. So one problem that does make it hard for us to determine exactly where they're coming from is that these cosmic rays are charged particles, meaning they are affected by electromagnetic fields. So as they pass through space, past galaxies and stars and whatnot, they do tend to bend and go in different directions. Now, neutrinos don't have this problem because they are not charged, so they can just kind of go right through everything. They follow much more of a straight line. And so because of that, it's thought that neutrinos might be an easier way to detect the source of cosmic rays because they're not being thrown around quite so much. In 2018, a neutrino detection at the IceCube Neutrino Observatory, which is also in Antarctica, pointed to a blazar some 4 billion years from Earth. And gamma ray measurements confirmed the blazar was flaring when the neutrino started its trip, so it's a likely culprit. And there could be other sources, multiple sources of high-energy cosmic rays, including colliding neutron stars and black hole collapses. Of all the mysteries that we talked about in this video, the source of cosmic rays is probably the one that's most likely going to be solved in the near future with new telescopes and detection equipment and whatnot. Or, as science tends to do, it might just bring up even more questions. And that's kind of the thing about space. The further you go into it, the deeper you look, the more questions pop up. I guess if you have an infinitely huge universe, you're going to come up with an infinite number of questions. Which I would argue is a good thing, because that means I'll never run out of things to talk about on this channel. So what's your best answer to some of these mysteries, or is there a space mystery that I didn't cover in this video? Talk about it in the comments. Now, one thing that's not a mystery is who makes the most comfortable underwear in the world. And that's because the answer is today's sponsor, Mack Weldon. I've talked about Mack Weldon on here before. Mack Weldon makes insanely comfortable underwear, and they make sure that it's insanely comfortable because they actually design their own fabric. They create a few different types of fabric, actually. You've got your dry knit, air knit, warm knit. They even have one called the Silver Series, which is actually treated with silver, so it's antimicrobial, which means they remain odor-free. I've got several pair of Mack Weldon boxer briefs, which I'll just leave that to your imagination. But they didn't just stop with underwear. They make shirts, shorts, pants, hoodies, jackets, hats, scarves, gloves, slippers. If you've got a body part, they've got clothing for it. The buying process is super easy online, they deliver fast, and they even offer a no questions asked refund if you don't like the first item you buy from them. And if you do like their products, and I think you will, and you'll want to buy more in the future, they've actually got a new loyalty program called Weldon Blue to make that even easier and to save you money. When you sign up for Weldon Blue, you get free shipping for life, that's level 1, but after you spend $200 or more, you get to level 2, which gives you a 20% off every order for the next year. So if you want to give them a try and see for yourself, just go to macweldon.com/Joe Scott. You'll get 20% off your first order, and if you don't like it for whatever reason, that first purchase, you return it, they'll refund it, no questions asked. Anyway, the link's in the description, but one more time, it's macweldon.com/Joe Scott. Link's down there. Keep your tender bits tender. I should say that's not their slogan. I just came up with that because I worked in advertising for 15 years and sometimes I just can't turn it off. Thanks to Mac Weldon for sponsoring this video, and a huge shout out to the Answer Files on Patreon that are keeping the lights on around here, helping me grow a team and forming a just really awesome community. I got some names I got to shout out real quick. We've got Troy Lewis, Blaze Buchanan, I think, Ryan Blackhawk, Samuel Reed, Curtis Ahrens, Sabbath Drake, Lexicon, Zach De Bernardi, Rand Wacker, Joshua Briner, Andrew Fisher, Christina Corbett, Jeffrey Lamarche, Andre, Sean O'Brien, and Anya Sonnendecker, I think. Thank you guys so much. If you'd like to join them, get early access to videos, exclusive live streams, and just join a really awesome community, you can go to patreon.com/AnswersWithJoe. Please do like and share this video if you liked it, and if this is your first time here, there's this video that might be up your alley, so you can check that out. You can check out any of the others that have my face on them down there, and if you like them and you want to see more, I invite you to subscribe. I do come out with videos every Monday. All right, cool, that's it for now. You guys go out there, have an eye-opening rest of the week, stay safe, and I'll see you next Monday. Love you guys. Take care.